So on the sacred day of Shivratri, today we're going to resume our series on gravitation. So today we're going to talk about central force, inverse square law, and about gravitational self-energy. So let's get started. So with central force we'll start. So what is central force? So thing is like central force is a force acting along the line joining center of two particles. If this is one particle and this is the other particle, then the force will act along this line, and it is dependent upon the distance between these two particles. Let it be r, then the force is dependent upon this r, so we can represent the force as this, showing that the force is actually dependent upon the distance between them, and therefore we can say that the force will also have a direction along this distance. So we will use a unit vector along the direction of the distance. So what will be the unit vector? Unit vector will be the distance vector divided by its magnitude, or simply r cap. This thing is known as r cap. This will be f r cap will be the force, and force is dependent upon this distance. So what will be the equation? Means how the force is dependent upon the distance. For central force, we use nth power law. I will get k by r square, and here if I put k equals to minus g m1 m2, then I will get gravitational force, and instead of g m1 m2, if I put q1 q2, then I will get electrostatic force. Means this is the general representation of the force, central force, and this is our gravitational force, which resembles to property of central force. Means gravitational force, electrostatic force, and central force. So here we know that force is negative gradient of potential energy, right? So if I integrate force, then I will get potential. Means force is basically minus du by dr, right? And potential energy will be equal to minus fd, integral of minus fdr, right? So now here I have the force minus g m1 m2 by r square. Now I want to calculate the potential energy, so I have to integrate this thing. So I will do it. Minus g m1 m2 by r square dr integration. So now if I integrate it, I will get minus r, integrating r to the power minus 2 will give us r to the power minus 1 by minus 1. Then negative sign will be positive, and we will get g m1 m2 by r, right, with a constant c1, and it is the potential energy. Basically this equation wants to say that if I am making a system of two particles having m1 m2 r distance apart, then this much energy will be stored in the system. And how the energy will be stored in this system? Because I will do some work, and this is the total work done stored inside the system as potential energy. And if I calculate here, if I put r equals to infinity, then this term will be equals to 0, and at infinity potential energy is also 0. So value of c1 will be equals to 0, right? This is known as putting initial conditions from mathematical physics. So basically this is the ultimate equation for potential energy. So now if I say that what I was telling, let me recall. So I was telling about, yes, the energy will be stored inside this system. And in a similar manner, if I change the constant, then potential energy for a system of charges or electrostatic potential energy will be Q1 Q2 by R. And if you have some change in system unit, then you will have a constant K. Now here is potential energy, and this is total potential energy for this system. And if you want to calculate potential energy due to M1 per unit mass, then you will simply divide this thing by M1 and then you will get the potential energy, potential at that point. Means potential energy per unit mass will give us the potential. We know the equation Gm by R. This is the potential due to mass m at a distance of r from it. Potential energy due to mass m at a distance r from it per unit mass. Okay, means basically potential is potential energy per unit mass. So now let's talk about principle of superposition. In the last lecture, in lecture of yesterday, I was talking about principle of superposition in electrostatics. The case is same, and basically here if I am having a system of particle M1, M2, M3, M4, then the interaction between M1 and M2 is not affected by M3 or M4, and the total force on M1 on M1 is vector sum of all the forces acting on M1. This is the principle of superposition. So now we are going to talk about, okay, let's talk a little bit more about central forces. I forgot to tell you about the special things about central forces. So here, if some particle is being acted upon by a central force, then the angular momentum will be conserved, because let's say we know the tau or torque on a particle will be equals to r cross f, the distance multiplied with the force, right? Here we know that force is a function of distance, like f r vector divided by its mod or r cap, and we can simply say that r cap cross f r cap. Here r cap have the same direction, means sin theta will be equals to sin 0, which will be equals to 0, means tau will be equals to 0. We know that tau is equals to dj by dt, means it is the torque is the rate of change of angular momentum. Here j is angular momentum. If this thing is equals to 0, means this thing is a constant, means the angular momentum is constant, sorry, not 0, constant, and angular momentum is r cross v, we know that. And if I take dot product of j and r, the position, the distance vector, then I will get it equals to 0. Here the r vector is perpendicular to angular momentum, and hence the entire motion is confined to a plane. So now I don't have enough space. Let me erase all these things so that we can talk about gravitational potential energy, gravitational self energy of a multi-particle system. Basically, in that case, we are going to do the same thing. Here we were talking about the force acting on m1, but in that case we will try to calculate potential due to all of the particles, and hence we will calculate the entire energy stored inside a particular configuration of particles. So first let me erase all these things. So now we are going to talk about potential energy or self energy of multiparticle system. So here if I draw a coordinate system and present here some particles, let it be m1, m2, m3, m4, m5 and these on. Then here they will have some force of attraction, and due to force of attraction we will have to do some work to get all of them into this configuration, and if we do some work on these particles, then this energy will be stored in this particular system, and the energy will be stored as potential energy of the system. So we will have to calculate the potential energy of the system. So force is equals to negative gradient of the potential energy. So we will integrate the force with respect to dr, so that we can get the total potential energy, and in the previous equation we got that potential energy will be equals to minus gm by r, right? So here actually negative sign of the potential energy indicates that the force is attractive. In case the force is repulsive, like that of electrostatics, if the charges are equal, then the sign will be positive, indicating that the force is repulsive. So force or yes, the force is repulsive. So now first let's consider this particular case, m1, m2, m3. Suppose we don't have m4 or m5, we have only these three particles. You can also do it for m4, m5 and many other particles, but here I am using the only three particles, so that equation will not be enough short that it cannot explain you about multi-particle system, and will not be so much large that it will take my time enough and make those clumsy calculations. So I have taken here three particles to tell you how these things work. You can do yourself adding more particles and calculating, but here I have three particles. So suppose I had only m1 here. I first tried to get m2 at a distance r12. I tried to get m2 at a position at a distance of r12 from m1 and put it here. So I have to do some work to do this thing. So the work will be integral of f dot dr. Here the work is stored at potential energy, so I can say that it is equals to u. So F is equals to minus g m1 m2 by r12. Here actually the force is attractive and the distance will be okay. Let me show you this thing. Here I am trying to, the force is attractive and going this way, and the displacement is this way, but as I am not trying it to accelerate, means I want all these things to be at with its constant velocity, means I don't want the m2 particle to accelerate while I take it to this position. So I have to apply an opposite force, because if the force is attractive and the force is being continuously acting upon the m2, then there will be acceleration and the total potential energy will not be equals to the work done, because from work energy theorem, if the velocity will change, the kinetic energy will change, and all of the things will not make us eligible to calculate this thing. Means if this particle will accelerate, then the potential energy will not be equals to the work done. Okay, so I have to apply a force opposite to this direction. So now the angle between them is 180 degree, means cos 180 equals to -1, and here minus gm1 m2 into dr into -1. Integrating it, minus sign will cancel, and then r12 square, and finally we will get g m1 m2 minus gm1 m2 by r12, right? Similarly, if m2 and m1 are here, now I want to bring m3 to a position where it is at a distance r13 from 1 and 23 from 2. Okay, in a similar manner we will calculate here the potential due to 1, due to 2, due to 1 on 2, and here potential on 3 due to 1 and 3 due to 2 will be equals to, we can use the same equation where g m1 m3 by r13 and g m2 m3 by r23. Okay, here we have three potential energy. The total potential energy stored in this system will be equal to sum of all these three. And now if I try to extend this case to nth particle, means r5 m4 m5 n6 and n number of particles, how the thing will look. First let us write the total thing here. Here I can take minus g common and sum the thing m1 m2 by r12 plus m1 m3 by r13 plus m2 m3 by r23, right? So now I want to represent it as using the summation sign. So I can write it as minus g summation. Now here we can see that there is a combination of masses m12 m13 m23, so I can write it as mi mj. Here I is not equals to j because potential at position of 1 due to m1 will sound absurd, so I is not equals to j, and here I is from 1 to 3, but if we want to calculate it for n number of particles, we can say that r equals to 1 to n. And here what about j? Here j is, we can say that j greater than I, or also you can write j less than I, because if you put all the conditions, then you will be able to see the thing. Here I put I equals to 1 and then search for a j, then j will be 2 and 3, m1 m2 and m1 m3. I got the first thing. Then I put I equals to 2. I start from 1, then I will go to I equals to 2. Then I will get 3 is greater than 2, so I can write m23. And then I will go to I equals to 3. No mass is number of mass. Here m3, the subscript denotes that m third mass or fourth mass, you can say, according to the number of masses. So here 3 there is no mass having the number, the subscript greater than 3, therefore it will not work for 3 and the total sum will be equals to this thing. And here R I j, right? Similarly, if you put the condition I greater than j, you will get the same result, because if you put I greater than j, then obviously 1 is not greater than anything, so you will just neglect 1. Then you will put I equals to 2. If you put I equals to 2, you will see that m1 is less than 1 is less than 2, so m12 will be this part. And then you put I equals to 3, you will see that 2 and 1 is less than 3, so you will get m23 and m13. Then you will get the same equation. Here you can do the same thing for 4 or 5 particles and get the same result, means get this particular result to be the same. And actually, if you first calculate the potential due to m1, you calculated it due to m1, then once you put m2, while doing this equation, here I have put the condition j greater than I and all, therefore we don't calculate it twice. But if I hadn't put this condition j greater than I, then we will be calculating every potential twice. So in that case, you can simply g summation j equals to 1 to n and I equals to 1 to n mi mj by rij multiplied with a half, because if you put j from 1, I not equals to 1, n not equals to j, if you put I equals to 1 and j equals to 2, and then once again if you put j equals to 1 and I equals to 2, you will get the same result. Actually you are calculating the potential twice, so you need to divide it by 2 to get the to calculate only once the potential energy. Actually this thing is happening because the gravitational force is conservative. It doesn't depend whether you first bring the m1 particle or first bring the m3 particle. It only depends upon which particle with what mass at what distance you put the particle. So here as it doesn't depend whether m1 is the first mass or m2 is the first mass, it will assume for m1 that m1 is first that came to this consideration, and it will also, while calculating it for m2, will consider that m2 was first, so it will also consider m12 and m21. That's why you have to divide it by 2. So remember that this force is a conservative force. And if this is a multi-particle system, these are discrete particles, but if you consider a rigid body, then how the things will go? The things will go the same way. Here you have to divide the rigid body into infinite number of small parts. And here, for if I calculate, if this particle was initially here, I added another particle this, so I did some work on it, and the work stored as potential energy, and then again another particle, and just I gathered all the particles into this particular configuration. So similarly I will need to calculate potential due to these small masses. So basically I am trying to break a big body into small particles. Then the potential will be the same way, g mi mj by rij, I equals to 1 to n, I less than or greater than j, this will be the self energy or potential energy of a rigid body. So we will calculate potential self energy, potential energy of galaxies and a rigid body or solid sphere in the next lecture. This is for today. Thank you.